Welcome to today's class. Today I'm going to start studying the full group of isometries of the upper half plane. So far we have established that every Mobius transformation that preserves the upper half plane bijectively is a Riemannian isometry of the upper half plane with respect to the hyperbolic Riemannian metric we have put on it. But it remains to determine the whole group of isometries. By this I may mean two things. Something I may mean is that maybe I want to find an explicit formula that governs the correspondence rule of any Riemannian isometry of the upper half plane. Right? Similarly to how the formula for Mobius transformations alpha z plus beta divided by gamma z plus delta governs the correspondence rule of any Mobius transformation. Right? So maybe I want to find an explicit formula for arbitrary Riemannian isometries. Or maybe I mean that I want to describe the whole group of isometries or the full group of isometries in terms of groups that I already know. Right? For instance, maybe I want to be able to describe the full group of isometries as a direct or semi-direct product of two groups that I already understand. Or maybe I want to put the full group of isometries in the middle of certain short exact sequence, for instance. So I'm going to do both things. And so the strategy I'm going to follow is that first I'm going to find an explicit formula for arbitrary Riemannian isometries of the upper half plane. So in other words, I'm going to find an explicit formula with the property that the correspondence rule of any Riemannian isometry is given by this formula. So describe the correspondence rule of arbitrary Riemannian isometries explicitly. And once I have done that, I'm going to use the kind of the form of this formula to see that the full group of isometries of the upper half plane is indeed a semi-direct product, and actually a semi-direct product that in the end turns out to be quite simple. Namely, it's going to be the semi-direct product of the Mobius transformations that preserve U bijectively by certain action of the group with two elements. So today what I'm going to be doing is finding an explicit formula for the correspondence rule of arbitrary Riemannian isometries of the upper half plane. Okay, so recall that we have decided to identify PSL2R, which is by definition this quotient, with the subgroup of mod plus C bar consisting of all those Mobius transformations that preserve U bijectively. And I'm going to use this identification without any further apology. Okay, so first of all, are there any Riemannian isometries outside PSL2R? So we know with this identification between this group and this group, we know that the elements of PSL2R are Riemannian isometries of the upper half plane. Now, of course, before starting any study, the first question is: do there really exist isometries outside PSL2R? Do there exist isometries that are really escaping the analysis we have done so far? And the answer is yes. Right? The answer is yes, and it's kind of so think about the inner product, the hyperbolic inner product. So anchored at any given point in U, right? So in other words, consider the hyperbolic Riemannian metric and consider how that inner product is defined at any given tangent plane at any point of U. So it's the usual dot product times the square of the imaginary part of the point I'm based at. Okay, so this means that if I apply some transformation, some function, let's say some diffeomorphism of U that preserves this imaginary part, so that somehow preserves the height of every point, I automatically have a Riemannian isometry. Okay, so for instance, this argument that I just said proves in particular that all horizontal translations are Riemannian isometries, right? This we already knew as well, because horizontal translations are Mobius transformations that preserve U bijectively, right? But somehow for horizontal translations, it is obvious that they preserve the inner product at every point, right? Because the imaginary part doesn't change. Okay, so now we know that Mobius transformations preserve the orientation, right? I mean, we know that their derivative is a matrix with a positive determinant. So in order to give an example of a Riemannian isometry not belonging to PSL2R, all we need is to be able to produce certain function, certain diffeomorphism of U that preserves imaginary parts, that doesn't move imaginary parts. And let's say that it changes, that it doesn't preserve orientation, right? So for instance, some diffeomorphism that preserves imaginary parts but has negative determinants, whose derivative has negative determinants somewhere or everywhere. Okay, so what comes to my mind is a vertical reflection, right? And the easiest vertical reflection, or the easiest one to describe by an explicit formula, is just vertical reflection on the imaginary axis. Right, think about it, and it's a diffeomorphism that has negative determinant, so it is not a Mobius transformation, and preserves imaginary parts everywhere. So it is a Riemannian isometry. Okay, so indeed, and here is the explicit formula, right? So it's a minus, it's a minus conjugation. So conjugation and then minus, right? Okay. So it does not belong to this one, right? To this group, and hence it also doesn't belong to this one, right? And here I'm being a bit pedantic, because strictly speaking, we have not yet proved that these two are equal. Right? But anyway, my argument shows that this reflection along the imaginary axis is an isometry that does not preserve orientation, and in particular, then it's not in PSL2R, so it's also not a Mobius transformation. Okay, so it really makes sense to start studying the full isometry group, Okay. Now, the strategy I'm going to follow in order to exhibit an explicit formula that governs arbitrary or formulae that govern arbitrary isometries, what I'm going to try and do is to force arbitrary isometries to be related to Mobius transformations and this one, right? Thinking kind of a priori that the full group of isometries, somehow the intuition tells me that by considering all isometries, the subgroup consisting of those that preserve orientation should have index 2 in the full group of isometries, right? And thinking that the Mobius transformations that preserve U, they are orientation preserving, and already thinking that they comprise the group of all orientation preserving isometries. Somehow I get the intuition that the full group of isometries can be described using only Mobius transformations and the single orientation reversing isometry, right? So since I have that intuition, I'm going to try to give an explicit formula by reducing arbitrary isometries to Mobius transformations and this specific reflection. Okay, now first of all, an exercise. This is an easy exercise. Show that if we take two different points in the positive part of the imaginary axis, and if I take any pair of points in U, but with the property that the distance between the points I'm taking is equal to the distance between the points I took in the positive part of the imaginary axis. So I have my 2 points in the imaginary axis, right? And I take other 2 points in U. The exercise is that if the distance between these two is equal to the distance between these two, then there exists a Mobius transformation that preserves U bijectively and sends these two to these two. This is an easy exercise. If you remember what I proved in the previous classes, in particular that given any 2 points in U, there always exists a Mobius transformation putting them in the positive part of the imaginary axis. If you start playing around with that I already proved, you can see that you can solve this exercise. Next exercise, that if we have an isometry, a Riemannian isometry. So remember that this R is for a Riemannian. Okay, so if we have a Riemannian isometry that fixes 2 points in the positive imaginary axis, 2 distinct points, then it fixes all points in the imaginary, in the positive part of the imaginary axis. So in order to deduce that an isometry fixes all points, every point in the positive part of the imaginary axis, to deduce that, it suffices to show that it fixes 2 distinct points on it. Okay. For instance, I mean, think about, we know 2 isometries that have the property of fixing the positive part of the imaginary axis point-wisely, right? Namely, the identity, but also this one, right? The reflection along the imaginary axis. Okay. But so far, we don't know that they are the only ones. Right? That's something to keep in mind. So far, there, in principle, there's still the chance that maybe there exists some third Riemannian isometry that fixes that fixes point-wisely the positive part of the imaginary axis, but is not either the identity nor this vertical reflection. At least for now, we don't know whether such a third Riemannian isometry with this property exists or not. Anyway, that doesn't worry me. And now let's start the analysis. Now that we have this kind of slightly technical exercises that, on the other hand, are not hard to solve. And now take an arbitrary Riemannian isometry of the upper half plane. And pick two distinct points, whichever you want, in the positive part of the imaginary axis. So any 2 points you want. You can fix, for instance, the point I and the point 2I, if you will. Any two distinct points will do the job. For those two distinct points, consider their images under the isometry. Okay. And what I'm going to do is, I don't know much about phi. But what I can do is that I can take a Mobius transformation that takes these 2 points back to where they came from. So I take such a Mobius transformation nu, such that it takes W1 back to W0 and Z1 back to Z0. And of course, somehow, right now, I don't know whether phi is related to nu or not. I don't know that. What I do know is that phi composed with nu, phi followed by nu, well, it fixes W0, of course, and fixes Z0, right? Because First, I go to W1 or to Z1, and then I go back. Okay, so it fixes this composition fixes two distinct points in the positive part of the imaginary axis. So we can deduce that it fixes every point in the positive part of the imaginary axis. Okay. Now, being an isometry that fixes every point in the positive part of the imaginary axis, I would like to be able to deduce that then this one is that this composition is either the identity or my reflection. I don't know that yet, right? So I really have to do some computations or give some argument as to why this indeed happens. That's what I'm going to do next. We know that on the positive part of the imaginary axis, we know what it does. So take an element in U outside the positive part of the imaginary axis and write it as A plus BI, of course with A and B reals, but of course B then is a positive, right? Because imaginary, it's in the upper half plane. So when I express W this way with A and B real, I know that B is positive, and also express its image on the decomposition as a real plus real times I. And also, since this one is in U, because I know that this one is an isometry from U to U, I also know that V is positive. So I know that B and D are positive. Just in case I need to use that fact, I am allowed to. And then what I'm going to do is to use this beautiful formula that we found, right? That related the hyperbolic cosine of the distance between 2 points with certain Euclidean information, right? and I'm going to use the fact that nu preceded by phi being a Riemannian isometry, it is also a distance isometry. Right? So that whenever I take any positive lambda, any positive real number lambda, well, I know that this number is equal to this number resulting from applying nu preceded by phi to both w and lambda I. And of course, using already the fact that nu preceded by phi applied to lambda I is lambda I. Okay, so I know that this is equal because this one is a Riemannian isometry, hence a distance isometry. And by the expression I prove, I know that this hyperbolic cosine is equal to this. Okay, and then I just substitute w equal to a plus bi. Right? So I arrive at this expression, of course. And in this other one, same thing, replacing nu phi of w by c plus di, I arrive at this expression, at this number. By the way, parenthesis, notice that when I showed this equality, I mean I based that equality on the fact that first this was shown to be invariant under the elements of PSL to R. So somehow here, thanks to the fact that this is a Riemannian isometry, I'm being able to see that this is preserved by this element that is not in PSL to R. Right? So somehow here this equality, the fact that phi is a Riemannian isometry, allows me to see that this is equal to this, even though I only showed that these expressions were invariant under PSL to R. In other words, now I'm somehow managing to show that these expressions are also invariant under any isometry. Anyway, so close parentheses. So what I arrive at is that this number is equal to this number, right? No matter which positive real number lambda I plug in. This is about to play a role. The fact that this equality holds no matter which positive lambda I take. And then of course, when I have this equal to this, then I can cancel this one, and then 2 lambda can cancel with this 2 lambda. So it cancels. And then I can pass then simply the d this way and the b this way. And when I do it and I expand these squares, I find that this minus 2 lambda bd appears in both sides of the equation. I can cancel. Then I realize that whatever is left, so you see this is positive times positive, and then plus positive times positive, plus positive times positive. So this is not 0, so I can divide by it. So I divide by it, and I have that this quotient is equal to 1. This quotient is equal to 1 for this w that I picked, right? And having expressed this one, the nu phi of w that way, but for every lambda, for every positive lambda. This holds for every positive lambda. So you see, think about you see the rational expression in kind of in the variable lambda, right? Or if you want x, where all the other numbers are constant. Right? So what this shows is that this quotient defines this constant function. In particular, when I take the limit when the variable tends to infinity, well, it's always equal to 1, right? So the limit is also 1. Okay, but in the limit, what happens is that the constant parts they all die out, and what I'm left is with the quotient of the coefficients that accompany the highest degree term in the variable, right? So what I arrive at when I let lambda tend to infinity is simply d divided by b equal to 1. So b is equal to d. Okay, b is equal to d. So when I come back here, I see that also this b can be cancelled with this d. And also I see that once I cancel that, then this is equal to this. So I can cancel it. And what I obtain is a squared is equal to c squared. So a is equal to plus or minus c. Okay, fair enough. Now, this means that for the w I took, for this point w I took, then either this happens or this happens. Right, because either you see b is always equal to d, that's no problem, and a is plus or minus c. So if a is c, then I'm in this situation. If minus a is c, I'm in this other situation, as you can easily check. But somehow my point is this I know for this particular w. At this moment, if I take another w, how do I know that the behavior is the same? So for instance, take certain w far away from the imaginary axis, in u, but far away from the imaginary axis. And let's say that for that one, I know that what happens is this one. Okay, and now go to some other place very far away also from the imaginary axis. How do I know that over there it is also this happens? How do I know that it's not the other one? And I know it by connectedness. So the formal argument is as follows. First, I leave you as an exercise to show that when you consider the positive quadrant of the complex plane, and in that positive quadrant, you split it into the set of all those elements that are sent to themselves, and the set of all those elements of the positive quadrant that are sent to the other side, and that these two are closed sets. That's quite easy, right? I mean, it's a quality, so it's very easy to see that this is a closed condition and this is a closed condition. And here, here I should have written conjugate. Okay. Once you know that it's a closed subset of the positive quadrant, excuse me. Well, then you notice that they are, of course, empty, and that their union is the whole positive quadrant. Right? So the connectedness, the fact that this one is connected, actually it's path connected. We see that indeed, it is not true that some elements of the positive quadrant satisfy this one and some others satisfy the other one, right? But that this is like these are kind of uniformly satisfied. Either every element in the positive quadrant satisfies the first one, or every element in the positive quadrant satisfies the other one. That's what I say here. This condition star. Okay, that's for the positive quadrant because the connectedness. How do I pass from that to knowing what I said happens in the entire upper half plane? Well, bijectivity, right? Because now on the positive quadrant, I either have this behavior or this behavior, right? So on the other quadrant, if in the positive quadrant I have this behavior, on the other quadrant contained in U, I cannot have this behavior. It has to stay then there, which is being given by the same rule in that case, right? And if in the positive quadrant what I have is this, then in the other quadrant I also must have that behavior, right? Because otherwise I would be violating bijectivity. So the fact that this one is bijective, that composition is bijective, allows us to deduce from star that either all the upper half planes obeys this rule, or all the upper half plane obeys the other rule. Okay, and now I'm in the position I wanted to be, because now I see that, for instance, here, if this is the case, then I know that for all W in the upper half plane, I have that phi of W is nu inverse of W, which means that then in that case, then phi is just the inverse of nu. But nu was a Mobius transformation. Right? So in this case, I can deduce that phi was necessarily a Mobius transformation. But on the other hand, if what happens is the second possibility, then then I can still do something, right? Because from this I know that phi of W is always equal to nu of minus W conjugate. So somehow phi is still controlled by a Mobius transformation, up to taking a conjugate, kind of by the value of a Mobius transformation on the not on W but on the reflected part. So it's kind of funny, right? I mean, the value of phi at a point is governed by what the Mobius transformation does in the other point. Anyway, let's take a matrix. In that case, let's take a matrix of determinant 1, that gives me nu inverse as a Mobius transformation. Okay, then, well, as I said, phi of W is nu inverse of minus W conjugate. And then, well, then I just plug this into the formula for nu inverse in terms of A, right? So it gives me this. And then what do I notice? Well, I notice that somehow this still looks like plugging in, a conjugate, this conjugate, into some Mobius type quotient, right? Where now the coefficients form a matrix of determinant -1, right? Because I know that alpha, beta, gamma, delta has determinant 1, so the coefficients here form a matrix that has determinant -1. Okay, so and once I consider that, then I say, okay, so maybe in order to obtain arbitrary isometries, I can kind of relax the condition that this must have determinant 1 to allowing it to have determinant -1, and then saying that in that case I plug in the conjugate instead of W itself, in order to still have a function that preserves U. Right? So what I have proved is this theorem, the theorem I was looking for, that if you give me a Riemannian isometry for the hyperbolic Riemannian metric, that we put on the upper half plane, then I'm in exactly one of two situations. Either my isometry was already a Mobius transformation preserving U bijectively, or or there is a matrix of determinant -1 with real entries, because here is real entries, right? So with the property that the correspondence rule of phi is given by, and you see here I'm already kind of these minus signs that make this have determinant -1. Somehow I'm already incorporating them in the numbers. And then in this case, then I have this, right? So in other words, what I'm saying is this A is somehow like not this A, right? I'm kind of, it's not this A. I'm rearranging the role of the variables. Anyway, okay, good. Now on the other hand, you see when we analyze this, you see this is equal to saying take first, take minus W conjugate, which already defined an isometry of the upper half plane. That's what I said, right? That's the first example I gave. Followed by this Mobius transformation. So not only it so happens that if you give me an isometry, then either it's a Mobius transformation or it's given by a matrix of determinant -1 and this correspondence rule. But indeed, in either of these two situations, I always have a Riemannian isometry. In other words, it does not happen that maybe there's something strange here that for some expressions I don't get a Riemannian isometry. That doesn't happen. So I have been able to describe explicitly all possible Riemannian isometries of U. Of course, there is the kind of the interesting question of whether the Riemannian isometries coincide with the distance isometries, right? So this I leave you as an exercise to think about it. What else is there to note or to notice? Yeah, now notice that from this theorem I can also deduce that, and so let me write it here. That whenever I have an isometry, a Riemannian isometry that preserves the orientation, that one is necessarily given a Mobius transformation. So now this theorem allows me to deduce that. Why? Because otherwise I would be in this situation, but in this situation, I just compute the derivative and I check that the derivative is a negative, it's a negative number. But the absolute value, I compute the derivative and I see that its determinant is negative. Its determinant as a, so this means that then if I have something that preserves the orientation, it has to be one of these. Okay, so now I know that. Okay, and well, for the next step is now to study then the structure of the full isometric group. In terms of this group that I already know, that I expect to have index 2 here, right? And, well, since I expect this one to have index 2 here, well, I would like to study the structure of the isometric group in terms of this one and the group with two elements. Okay, so in order to start to make that study possible, I defined this kind of extended special linear group to be the group of all real matrices that have determinant 1 or minus 1. So we'll start here. Okay, so and the theorem then tells us that by assigning to the matrices with determinant 1 the corresponding Mobius transformation, and to the matrices with determinant minus 1 the function given by this rule, we have a surjective function that to each matrix associates something that happens to be an isometry. Okay, and that this function is surjective, right? So the fact that I have a function here is actually this part, and the fact that it's surjective is the content of the theorem. And I think I will leave you as an exercise to show that this is a group homomorphism. So maybe let me say exercise. Exercise. Mu tilde is a group homomorphism. And it's exercise, I believe it's exercise 63, no, 62. I know 63, yes, because here's 63. Okay, and then tomorrow I'm going to continue with the description of this group in terms of this group and the group with one element. I'm going to see that it's a semi-direct problem.